Somewhere near the constellation Canes Venatici, light that left its source before the Earth had continents in their current shape, is only now reaching our telescopes, radiating from a single point brighter than an entire galaxy of stars. That point is a black hole named TON 618, and by some estimates it holds the mass of 66 billion suns inside a boundary smaller than our solar system's outer reaches. This episode traces how astronomers arrived at that number, starting from the simple physics of an ordinary collapsing star, building up through the supermassive black hole anchoring our own galaxy, and finally reaching the strange, oversized class of objects that TON 618 represents, one of the most extreme things any telescope has ever detected. Start with something ordinary, throw a ball straight up, and gravity pulls it back down. Throw it faster and it goes higher before falling. Throw it fast enough, about 11.2 kilometers per second from the surface of the Earth, and it never comes back at all. That speed is called escape velocity, the minimum speed needed to break free of a body's gravity forever. Every object with mass has an escape velocity. The Earth's is a little over 11 kilometers per second. The Sun's, from its visible surface, is around 618 kilometers per second. Both numbers depend on the same two things: how much mass is doing the pulling, and how far away you are starting from. Now shrink an object without losing any of its mass. Pack the same amount of matter into a smaller and smaller sphere, and its surface gravity climbs, because you are standing closer to all of that mass at once. The escape velocity climbs with it. There is no theoretical limit to how far this can go, and physics allows a startling endpoint. An object compressed enough that its escape velocity, at the surface, exceeds the speed of light itself, roughly 300,000 kilometers per second, the fastest anything in the universe can travel. At that point nothing, not a spacecraft, not a photon, not even light, can climb back out. That boundary, the point of no return, is called the event horizon. Inside it is a black hole. The idea is not new speculation. In 1783, the English clergyman and scientist John Michael reasoned, using ordinary Newtonian gravity, that a star far larger than the Sun, but with the Sun's density, would have an escape velocity exceeding the speed of light, and its light would not reach an outside observer. He called the idea a dark star. The French mathematician Pierre-Simon Laplace proposed something similar a few years later. Both were working more than a century before anyone knew what such an object would actually do to space and time nearby. But the essential insight, mass concentrated enough traps its own light, was already there. It took Albert Einstein's 1915 general theory of relativity, and the physicist Carl Schwarzschild's exact solution to it the following year, to describe the effect properly. Schwarzschild found that every mass has a radius, now called the Schwarzschild radius, at which this collapse into an inescapable boundary would occur. The term black hole itself is newer still. The physicist John Wheeler popularized it in 1967, 2 centuries after Michel's dark star, to describe an object with no light, no matter, and seemingly no information able to climb back out. To grasp how strange the density has to be, consider the numbers from the other direction. Compress the Earth down to about 9 millimeters across, roughly the size of a peanut, and the escape velocity at its new surface would exceed the speed of light. Nothing in the known universe can do that to the Earth. Compress the Sun down to about 3 kilometers across, and the same thing would happen to it. Neither of those things will happen to the Earth or the Sun. But a star many times more massive than the Sun, at the end of its life, can do something very much like it to itself, using nothing but its own weight. A black hole itself is not a hole in the usual sense, and it is not a hungry mouth reaching out to grab anything nearby. Outside its event horizon, a black hole's gravity behaves exactly like the gravity of any other object of the same mass. If the Sun were somehow replaced this instant by a black hole of the same mass, Earth's orbit would not change at all. The Earth would keep circling at the same distance for the same reason it does now. Gravity pulling in proportion to mass and distance. Nothing more exotic. What makes a black hole different is only what happens once something crosses that one specific line, the event horizon, drawn by the Schwarzschild radius. Outside it, ordinary gravity. Inside it, a one-way boundary that nothing recrosses. That distinction matters, because the story ahead is going to describe some genuinely staggering numbers, masses in the billions of suns, boundaries wider than entire planetary systems. It is easy, faced with numbers like that, to picture something like a cosmic drain pulling in everything nearby. That picture is wrong at every scale, from the smallest stellar mass black hole to the largest ultramassive one this story will eventually reach. Keep the correct picture instead, a boundary, drawn by mass and by the Schwarzschild radius, past which the ordinary rules of escape stop applying, but not 1 inch before it. So the real question ahead is not how something reaches out and grabs matter. It is how much mass can end up packed behind one of these boundaries, and how large that boundary can become. The next step is where nature actually builds the smallest, most common kind of black hole. Not a shrinking Earth or a shrinking Sun, but a dying star with a core made of iron and nowhere left for that iron to go. A star spends almost its entire life fighting gravity with the products of its own furnace. In its core, hydrogen nuclei fuse into helium, releasing energy that pushes outward as light and heat, exactly balancing the crushing inward pull of the star's own mass. Fusion is the engine, gravity is the load. For a star like the Sun, hydrogen fusion can hold that balance for roughly 10 billion years. For a star born with 20 or 30 times the Sun's mass, the same fight is fiercer and far shorter, sometimes only a few million years, because a heavier star burns through its fuel at a punishing rate to support its own greater weight. Eventually the fuel runs out, but not all at once. A massive star burns through its fusion fuels in stages, like a furnace working down through cheaper and cheaper wood. Hydrogen fuses to helium. Once the hydrogen in the core is exhausted, the core contracts and heats further, and helium begins fusing into carbon and oxygen. That exhausts and the core contracts again, heating further still, until carbon fuses, then neon, then oxygen, then silicon, each stage shorter than the last, each leaving behind a slightly heavier ash. The final stage produces iron. Iron is where the fight ends because fusing iron nuclei into anything heavier does not release energy, it consumes it. For the first time in the star's life, the core has no fuel left that can push back. Without fusion's outward pressure, gravity wins immediately and completely. The iron core, by this point often close to the mass of the Sun, packed into a region smaller than the Earth, collapses in well under 1 second. As it falls inward, its density rockets past anything fusion ever produced, and the collapse does not stop cleanly. It overshoots, rebounds, and slams outward again as a shockwave, tearing through the star's remaining outer layers and blasting them into space at tens of thousands of kilometers per second. Seen from a distant galaxy, that blast is a supernova, briefly outshining every other star in its home galaxy combined. It is one of the most energetic events general relativity and nuclear physics together allow. What happens to what is left behind depends entirely on how much mass survives the explosion. Matter resists further compression through quantum mechanical effects that have nothing to do with fusion or heat. Electrons packed tightly enough refuse to occupy the same state as one another, a rule called the Pauli exclusion principle, and that refusal creates an outward pressure called electron degeneracy pressure, strong enough to halt the collapse of a star's remnant, provided the remnant is not too heavy. That limit was calculated by the astrophysicist Subramanian Chandrasekhar in the 1930s, and now bears his name, the Chandrasekhar limit, roughly 4 times the mass of the Sun. A remnant lighter than that stabilizes as a white dwarf, an Earth-sized ember slowly cooling for billions of years. Push past the Chandrasekhar limit, and electron degeneracy pressure is no longer enough. The collapse continues until electrons and protons are forced together into neutrons, and a new quantum resistance takes over, neutron degeneracy pressure, which can hold the line up to somewhere around 2 to 3 times the mass of the Sun, an approximate boundary called the Tolman-Oppenheimer-Volkoff limit, because the exact number depends on details of nuclear physics still being refined. A remnant in that range becomes a neutron star, an object with the mass of a star packed into a sphere only about 20 kilometers across, so dense that a teaspoon of its material would weigh billions of tons. Beyond roughly 2 to 3 times the Sun's mass, there is no known force left that can hold the line. Gravity has already beaten fusion, then electron degeneracy, then neutron degeneracy, and nothing else in known physics stands between an ever-shrinking mass and the Schwarzschild radius calculated a century earlier. The collapse simply continues, past the density of a neutron star, past every quantum flaw that stopped it before, until the object's own escape velocity crosses the speed of light. A stellar mass black hole has formed, typically somewhere between about 5 and a few dozen times the mass of the Sun, born in less than a second, from a star that had shone for millions of years. That is the small end of the scale, the most common and best understood way a black hole is built. It is also, as the rest of this story will show, staggeringly far from the largest. What forms next, and what happens once matter actually crosses that final boundary, is where the story turns from stellar death to the deep structure of space and time itself. A black hole has just formed, in this story a stellar mass one, and its event horizon, the point of no return boundary, calculated from the Schwarzschild radius, now exists as a real feature of space, roughly 30 kilometers across for a remnant around 10 times the Sun's mass. Nothing marks this boundary. There is no wall, no shimmer, no surface a spacecraft's hull would strike. If an astronaut, purely as a thought experiment, fell feet first toward this object, nothing about the boundary itself would announce that it had been crossed. From her own perspective, in her own reference frame, she would sail through the event horizon at a finite, unremarkable moment, feeling nothing special happen at that exact instant. What she would feel, well before reaching the horizon, is something else entirely, a stretching force called tidal gravity, the same effect that raises ocean tides on Earth, but here taken to an extreme. Tidal gravity arises because gravity's pull is stronger on the near side of an object than the far side. Falling feet first toward a small stellar mass black hole, the astronaut's feet, closer to the black hole, would be pulled far harder than her head, and the difference would stretch her along the direction of fall while compressing her sideways. Astrophysicists call this spaghettification. For a black hole only a few times the Sun's mass, this stretching becomes lethal long before the event horizon itself, sometimes thousands of kilometers out. That detail matters, because it will matter again, much later in this story, when the black hole under discussion is not stellar-sized, but almost inconceivably larger, and the same tidal forces behave very differently. To anyone watching from a safe distance, the astronaut's fall would look nothing like her own experience. General relativity predicts that time itself runs slower in stronger gravity, an effect called gravitational time dilation, confirmed experimentally many times over, including in the everyday operation of satellite navigation systems, which must correct for it to keep accurate time. Near a black hole's event horizon, the effect becomes extreme. From the distant observer's point of view, the astronaut's fall would appear to slow down more and more as she approached the horizon, her image growing dimmer and redder. The light from her suit stretched to longer wavelengths, an effect called gravitational redshift, until she appeared to freeze at the boundary and fade from view entirely, never quite visibly crossing it. Both descriptions are correct at the same time for the same event. That is not a contradiction. It is one of general relativity's genuine, well-tested strangenesses that time and simultaneity themselves depend on where you are standing. Once inside the event horizon in the astronaut's own experience, the geometry of space and time changes in a way words strain to describe. Falling toward the center is, in a real physical sense, no longer optional or reversible in the way that falling toward Earth's center is. Every future path, for anything and anyone inside, leads only inward toward a region called the singularity, where the equations of general relativity predict the density becomes infinite. Most physicists treat that infinity as a signal that general relativity itself breaks down there, rather than as a literal description of nature, because reconciling gravity with quantum mechanics at such extreme densities remains one of the unsolved problems in physics. What actually happens at the center of a black hole is genuinely unknown. No experiment has ever probed it, and no accepted theory yet describes it. The part of the story that is well tested is everything up to and including the event horizon itself. There is also a second, less absolute boundary worth naming, because pictures of black holes rely on it, the photon sphere, a region where gravity is strong enough to bend light into a closed loop, curving all the way around the black hole. It sits just outside the event horizon, at 1.5 times the Schwarzschild radius for a non-rotating black hole. Light grazing a black hole just outside the photon sphere gets bent, sometimes dramatically, producing the warped, ring-like glow seen in real photographs of black holes, an effect this story returns to when it reaches those photographs directly. None of this, spaghettification, time dilation, the singularity, or the photon sphere, changes the basic outer picture established earlier. Gravity outside the horizon behaves normally. The drama is entirely a property of the boundary and what lies within it. What changes from black hole to black hole is only the numbers, how much mass, how large the horizon, how violent the tidal forces at that horizon, and it is precisely those numbers, scaled up from a stellar remnant to something almost incomprehensibly larger, that the rest of this story is building toward. The event horizon this story has been describing, the one an infalling astronaut would cross without any final signal, comes in a specific size for a specific mass, and it is worth pausing on just how small that size actually is for the ordinary stellar mass black holes formed by dying stars. The Schwarzschild radius scales directly with mass. Multiply the mass by 10, and the radius multiplies by 10 as well, a clean relationship despite the extreme physics behind it. For an object with the Sun's mass, the Schwarzschild radius works out to about 3 kilometers. Double the mass, and the radius doubles to about 6 kilometers. A typical stellar mass black hole, the kind formed from the collapse described in the previous chapter, weighs somewhere between about 5 and 20 times the mass of the Sun, giving event horizons somewhere between roughly 15 and 60 kilometers across. Picture that against something familiar. An event horizon 30 kilometers across, roughly the size expected for a black hole around 10 times the Sun's mass, would fit comfortably within the boundaries of a mid-sized city, with room to spare on every side, and all of that city-sized boundary would enclose a mass 10 times greater than the entire Sun. The density implied is difficult to state in any way that feels intuitive. Matter this compressed no longer resembles matter as encountered anywhere else, not a star, not a planet, not a neutron star, but something whose properties are described entirely by 3 numbers, its mass, its spin and its electric charge, a striking result in general relativity sometimes summarized as no hair, meaning a black hole retains no other distinguishing feature of whatever fell into it. Objects this small and this dark cannot be photographed directly, not with any telescope built or planned. Every stellar mass black hole known has been found indirectly, through its effect on something visible nearby. The first strong candidate, a source called Cygnus X1, was identified in the 1970s, a bright, compact source of X-rays in orbit with a visible blue supergiant star. The two locked in a mutual orbit lasting about 5.6 days. The X-rays come from gas pulled off the visible star, heated to millions of degrees as it spirals inward toward the unseen companion, and the orbital motion of the visible star lets astronomers calculate the mass of the thing it is orbiting, roughly 21 times the mass of the Sun in Cygnus X1's case, far too heavy for any known star that emits so little visible light of its own. That combination, an X-ray source paired with an invisible but gravitationally dominant companion, became the template for identifying stellar mass black holes for decades. A second, entirely different method arrived in 2015, when the Laser Interferometer Gravitational Wave Observatory known as LIGO detected a signal from 2 black holes, roughly 36 and 29 times the mass of the Sun, spiraling into each other and merging into one, releasing a burst of gravitational waves, ripples in spacetime itself predicted by Einstein a century earlier, and finally measured directly for the first time. That single merger, and the roughly 90 similar ones LIGO and its partner observatories have detected since, opened an entirely new way to weigh black holes that never emit a single photon of light, by listening to the spacetime ripples their collisions produce. Both methods, X-ray binaries and gravitational waves, keep turning up black holes clustered in the same rough range, from about 5 to somewhere in the low hundreds of times the Sun's mass. That range represents the size of black hole a single dying star, however massive, can plausibly produce in one collapse, a real limit set by how much mass a star can hold onto before shedding the rest in stellar winds and supernovae. It means that the numbers coming later in this story, tens of millions, then billions of solar masses, cannot come from a single star's death at all. Something else has to be doing the building over a much longer stretch of time, and that something is where the story turns next. A single collapsing star, as the previous chapter showed, tops out at a black hole weighing at most a few hundred times the mass of the Sun. Yet the rest of this story is about to describe black holes weighing millions, then billions, of solar masses. Bridging that gap is not a matter of one dramatic event. It is the accumulated result of 2 much slower processes working together over enormous stretches of cosmic time. Accretion, the steady swallowing of surrounding gas and dust, and mergers, black holes combining with other black holes as galaxies themselves collide and merge. Accretion is the more straightforward of the two, though it is not unlimited. When gas falls toward a black hole, it rarely falls straight in. Instead, it spirals inward through a flattened, superheated structure called an accretion disk, friction and compression heating the infalling matter to millions of degrees before it finally crosses the event horizon. That heated gas radiates enormous amounts of light, and that light pushes back outward on the very gas trying to fall in, a form of radiation pressure. There is a natural balance point, called the Eddington limit, named after the astrophysicist Arthur Eddington, where the outward push from radiation exactly balances the inward pull of gravity on the infalling gas. A black hole accreting faster than this limit would blow its own fuel supply away before it could fall in. The Eddington limit does not forbid faster growth entirely. Some theoretical models allow brief, disk-shielded episodes of faster feeding, but it sets a rough speed limit on how quickly accretion alone can grow a black hole's mass over time. Mergers add mass in sudden jumps rather than a steady trickle. Galaxies collide over cosmic history, pulled together by gravity across distances of hundreds of thousands of light-years, a process still ongoing. The Milky Way itself is on a slow collision course with the neighbouring Andromeda galaxy, an encounter expected in roughly 4 billion years. When two galaxies merge, the supermassive black holes at each of their centres are eventually drawn together as well, and given enough time they merge into one larger black hole, releasing a final burst of gravitational waves like the smaller stellar mass mergers LIGO detects, but on a scale current instruments cannot yet measure directly. Even with both processes running continuously, growing a black hole from a few hundred solar masses to billions takes a very long time, and that creates a genuine puzzle in modern astronomy. Telescopes have found quasars, the brilliant accretion signatures the next chapters return to, powered by black holes already weighing close to 1 billion solar masses, from a time when the universe itself was less than 1 billion years old. Growing a black hole that large that quickly, even accreting continuously at the Eddington limit, is difficult to explain if the starting point was only a few hundred solar masses left behind by an early massive star's collapse. That difficulty has led astrophysicists to propose a second possible starting point. Rather than a modest stellar remnant, some black holes may have begun as heavy seeds, forming directly from the collapse of enormous, especially pristine clouds of gas in the very early universe, skipping the star formation stage entirely and starting the growth race already tens of thousands or more of solar masses ahead. Both pathways, light seeds slowly built up and heavy seeds starting larger, remain active areas of research, and astronomers do not yet know which one, or what mixture of both, actually built the earliest and largest black holes observed. What is not in dispute is the destination this combination of accretion and merging reaches, given enough time. Essentially every large galaxy studied closely enough, including the Milky Way, harbours a supermassive black hole at its centre, millions to billions of times the mass of the Sun, sitting at the bottom of the galaxy's gravitational well, like a seed around which the rest of the galaxy's structure appears to have organised. One of those supermassive black holes is close enough for direct study in extraordinary detail. The one at the centre of the galaxy this story's listener happens to live in. Every galaxy examined closely enough seems to hold one of these objects at its centre, and the nearest example by a wide margin sits at the centre of the Milky Way itself, about 26,000 light-years from Earth in the direction of the constellation Sagittarius. Astronomers call it Sagittarius A star, often shortened to SGR A star, and unlike almost everything else in this story so far, it can be, and has been, observed directly in remarkable detail because it is so much closer than any other supermassive black hole. The first hint of something unusual at the galactic centre came in 1974, when radio astronomers Bruce Ballack and Robert Brown detected a compact, unusually bright source of radio emission there, distinct from the ordinary glow of stars and gas nearby. For decades afterward, its exact nature and its mass remained uncertain, obscured behind thick clouds of interstellar dust that block visible light from reaching Earth along that line of sight. The breakthrough came from infrared observations, which passed through that dust far more easily, and from tracking year after year the individual stars orbiting closest to the galactic centre. One star in particular, catalogued as S2, became the key to weighing the darkness at the centre of that orbit. S2 follows a tight, elongated orbit around Sagittarius A star, completing one full circuit in a little over 16 years, a span short enough that two research teams, one led by Andrea Ghez in the United States and one by Reinhard Genzel in Germany, were able to track its entire path multiple times using large ground-based telescopes fitted with adaptive optics, a technology that corrects in real time for the blurring effect of Earth's atmosphere. From the shape, size and timing of that orbit, using the same orbital mechanics that let astronomers weigh planets around the Sun, both teams independently calculated the mass of the object S2 was orbiting, about 4.3 million times the mass of the Sun, packed into a region no larger than our own solar system. There was no visible star, no visible anything, at the point all those orbits converged on. Ghez and Genzel shared half of the 2020 Nobel Prize in Physics for that work. A supermassive black hole was, at that point, the only object consistent with the mass, the size, and the total absence of light. Confirmation, in the most direct sense telescopes currently allow, came in 2022 when the Event Horizon Telescope collaboration, an international network of radio observatories spread across the globe and linked together to act as a single enormous telescope, released the first direct image of Sagittarius A star, a dark central shadow ringed by the glow of superheated gas swirling just outside it. It was the second such image the collaboration produced, following an image of the supermassive black hole at the center of the far more distant galaxy M87 in 2019, but Sagittarius A star's image was, in a real sense, harder to make, because matter orbits it much faster, on timescales of minutes rather than days, and the picture had to be built from data collected, while the source itself was actively changing shape. Set beside the stellar mass black holes described earlier in this story, some tens of kilometers across, Sagittarius A star's proportions are almost impossible to hold in mind at once. Its event horizon spans roughly 24 million kilometers in radius, about 16 times the average distance from the Earth to the Sun, a boundary that would comfortably swallow Mercury's entire orbit and reach partway to Venus, and 4.3 million solar masses, though it sounds enormous, turns out to be a fairly ordinary supermassive black hole by the standards of the rest of the universe. Other galaxies, studied at far greater distances, have been found to house central black holes tens, hundreds, even thousands of times heavier than Sagittarius A star, and understanding how astronomers can even measure the mass of something so distant that no individual orbiting star can ever be tracked is the next piece this story needs before it can reach the object it has been building toward. Sagittarius A star could be weighed with unusual precision because it is close enough for individual stars orbiting it to be tracked one by one, year after year, an approach that works for perhaps a handful of the very nearest galaxies and nothing farther. Almost every other black hole mass estimate in astronomy, including the one this story is building toward, has to be made a different way, using indirect signatures that stand in for an orbit no telescope could ever resolve. The most common method for nearby galaxies relies on the same orbital mechanics used for Sagittarius A star, but applied to the collective motion of many stars or a disk of gas at once, rather than tracking one star individually. Spectroscopy, the technique of splitting a source's light into its component wavelengths, reveals the speeds of stars or gas clouds through the Doppler effect, the same shift in pitch a passing ambulance siren undergoes, but applied to light instead of sound. Measuring how fast stars near a galaxy center are moving, and how that speed changes closer in, lets astronomers infer the mass concentrated at that center in exactly the same way Ghez and Genzel used S2's orbit, just averaged over a whole population of stars rather than one. For galaxies too distant to resolve individual stellar orbits at all, a striking shortcut emerged in the late 1990s and early 2000s. The mass of a galaxy's central black hole turns out to correlate closely with an entirely separate, easier-to-measure property, the average speed at which stars move throughout the galaxy's central bulge, called the velocity dispersion. This relationship, known as the M-sigma relation, lets astronomers estimate a black hole's mass just from how fast stars are moving across an entire galaxy, without resolving any individual orbit near the black hole itself. It is not perfectly precise, but it has held up remarkably well across a huge range of galaxy types and distances, and it strongly suggests that a galaxy's central black hole and its surrounding population of stars grow together, shaped by the same history. None of these methods work for a black hole billions of light years away that is actively feeding, a quasar so bright it outshines its entire host galaxy and drowns out the starlight astronomers would otherwise need to measure. For those objects, astronomers turn to reverberation mapping. A quasar's central engine, the hot accretion disk itself, flickers and varies in brightness over days to weeks, driven by turbulence in the infalling gas. Surrounding that disk at a larger radius sits a region of fast-moving gas clouds called the broadline region, which absorbs some of that light and re-emits it as characteristic emission lines. Because light takes time to travel, the broadline region's emission lags behind the disk's own flickering by a measurable delay, sometimes days, sometimes weeks, and that delay is directly a light travel time measurement of the broadline region's radius, an astronomical distance measured the same way sound and echo measure the distance to a canyon wall. Combine that radius with the speed of the gas clouds themselves, Measured from how broad and Doppler smeared their emission lines appear, and the same orbital physics used everywhere else in this story, gravity balanced against orbital speed, yields a mass for the black hole at the centre. This is called the virial mass method, and it has been calibrated carefully against the more direct techniques in nearby galaxies, where both can be measured. For the most distant, most extreme objects, however, quasars whose light left them 10 billion years ago or more, reverberation mappings repeated. Weeks-long monitoring is often impractical, and astronomers instead rely on a faster shortcut, a single epoch virial estimate, using an established relationship between a quasar's overall brightness and the expected size of its broad line region, combined with one measurement of an emission line's width, to estimate a mass from a single observation rather than a full monitoring campaign. That shortcut is genuinely useful, and it is the method that produced the mass estimates for the single most extreme object this story has been building toward. It is also, honestly, the least precise method described so far, carrying real uncertainty, commonly cited as roughly a factor of 2 or 3 in either direction, because it depends on assumptions about the geometry and behavior of gas clouds that astronomers cannot directly observe at that distance. Every number that follows about that object's mass should be read with that honest uncertainty attached. With the toolkit in place, the story can finally turn to the object itself. That toolkit exists because some black holes make themselves loud enough to measure from billions of light years away, and the loudest of all are quasars, a name whose history is worth pausing on because it captures how strange these objects looked when they were first found. In the early 1960s, radio astronomers catalogued a number of compact sources of radio emission that, when examined with optical telescopes, appeared to coincide with faint, star-like points of light, objects that looked for all the world like ordinary stars in visible light, but blazed brightly at radio wavelengths, utterly unlike any known star. They were named quasi-stellar radio sources, star-like but not stars, soon shortened to quasars. In 1963, the astronomer Martin Schmidt examined the spectrum of one of these objects, catalogued as 3C273, and found emission lines at wavelengths that made no sense for any nearby star, until he realized the lines matched ordinary hydrogen, just shifted dramatically toward longer, redder wavelengths, an effect called redshift, caused by the expansion of the universe stretching light as it travels across cosmic distances. The amount of redshift told him the object was roughly 2 billion light-years away. And for something that faint-looking star-like point to be visible at all across that distance, it had to be extraordinarily luminous, tens of trillions of times brighter than the sun. That single realization changed how astronomers understood the universe's most extreme objects, and it is now understood that quasars are exactly the kind of supermassive black hole this story has been describing, caught in the act of actively feeding. The engine behind that brightness is the accretion disk itself, described in an earlier chapter as the flattened structure gas spirals through on its way toward a black hole's event horizon. In a quasar, that disk is feeding at a rate substantial enough, often close to the Eddington limit described earlier, that the innermost regions of the disk, compressed and sped up by the black hole's intense gravity, heat to temperatures of hundreds of thousands of degrees, radiating strongly across ultraviolet and X-ray wavelengths as well as visible light. That radiation pours outward from a region astonishingly, no larger than our own solar system, a scale so small compared to an entire galaxy's worth of stars that a quasar's light source is in effect a single tiny unbelievably bright point, exactly what made 3C273 look star-like in the first place. Some quasars add a second spectacular feature, narrow focused streams of charged particles called relativistic jets, launched from the immediate vicinity of the black hole and accelerated to speeds approaching that of light itself, extending outward sometimes for hundreds of thousands of light-years, far beyond the boundaries of the host galaxy entirely. The exact mechanism that launches these jets is still an active area of research, involving the black hole's spin and powerful magnetic fields twisted up in the surrounding disk, and astronomers do not yet have full agreement on every detail. What is well established is that a jet's presence or absence has more to do with a black hole's spin and magnetic environment than with its mass alone. Some of the most massive black holes known produce no visible jet at all, while some comparatively modest ones do. Put the accretion disk's light and, in some cases, the jets together, and the total output of an actively feeding quasar can genuinely outshine every star in its host galaxy combined, sometimes by a factor of hundreds or thousands, a single point of light at a galaxy's centre outcompeting tens of billions of individual suns. Most quasars, weighed by the methods described earlier, cluster in a range from a few million to a few billion solar masses, but a small number push past even that range into a category so extreme that astronomers gave it its own name, and it is that category the story turns to next. The term supermassive black hole covers an enormous range on its own, from Sagittarius A stars' 4.3 million solar masses up through hundreds of millions, even a few billion, found at the centres of larger galaxies. Somewhere past a few billion solar masses, astronomers begin using a separate, informal term, ultramassive black hole, for a category so far beyond ordinary supermassive black holes that some researchers question whether the same growth processes described earlier, steady accretion and galaxy mergers, can even fully explain how they got that large within the age of the universe. There is no single universally agreed threshold for where supermassive ends and ultramassive begins. Different researchers have drawn the line anywhere from about 5 billion to about 10 billion solar masses. What is not in question is that objects clearly past even the higher of those lines exist, and a handful have been measured with genuine confidence. Using the same direct stellar and gas dynamics methods described in an earlier chapter, rather than the less certain single-epoch virial estimates reserved for the most distant quasars. One of the best measured examples sits at the centre of a galaxy called Holmberg 15A, the brightest galaxy in a cluster of galaxies roughly 700 million light-years away. In 2021, astronomers using the Very Large Telescope in Chile modelled the motion of stars throughout that galaxy's core in detail, and arrived at a black hole mass of roughly 40 billion times the mass of the Sun, one of the most massive black holes ever measured by direct dynamical methods rather than by an indirect virial estimate. Its event horizon alone, at that mass, would span a region roughly the size of our entire solar system out past the orbit of Pluto. Another striking case is a system called OJ287, notable less for a single measured mass than for the method used to find it. OJ287 shows a distinctive repeating pattern of bright optical outbursts roughly every 12 years, a periodicity that has held up across more than a century of archived observations, including old photographic plates dating back to the 1890s. The leading explanation is that OJ287 hosts not one black hole but two, a primary weighing an estimated 18 billion solar masses and a much smaller companion, around 150 million solar masses, locked in a tight elongated mutual orbit. On each close approach, the smaller black hole is thought to punch through the larger one's accretion disk, twice per orbit, triggering the bright flares astronomers have tracked for well over a century. If that model holds, OJ287 offers something almost nowhere else in astronomy does. A black hole mass measured not from stellar orbits or emission lines, but from the precisely timed rhythm of a predicted future collision, tested and confirmed against real observations. These examples establish two important points before the story reaches its central subject. First, ultramassive black holes tens of billions of times the Sun's mass are real, confirmed objects, not a theoretical curiosity. Several are known with reasonable confidence. Second, the best measured ones tend to be relatively nearby, hundreds of millions to a few billion light-years away, close enough for the direct dynamical methods to work. The single object at the centre of this episode is neither nearby nor measured by those direct methods. It sits more than 10 billion light-years away, far too distant and far too faint in its underlying galaxy for any stellar orbit to ever be resolved, and everything known about its mass rests instead on the single epoch virial method described earlier. With all of the honest uncertainty that method carries, understanding that constraint is essential to understanding every number the rest of this story is about to give. In 1957, astronomers working at the Tonantzintla Observatory in Mexico, conducting a photographic survey searching the sky for objects with an unusual excess of blue light, a technique commonly used at the time to hunt for hot white dwarf stars, catalogued an otherwise unremarkable point of light as entry number 618 in their survey, giving it the designation TON 618, TON simply abbreviating the observatory's name. On the photographic plates of the day, it looked exactly like what the survey was designed to find, a compact, unusually blue star, one among many similar entries in the same catalogue, in the direction of the constellation Canes Venatici, the hunting dogs, a modest, little-noticed group of stars near the more famous Big Dipper. For more than a decade, that classification stood. Nothing about a routine blue excess catalogue entry demanded further attention. Surveys like this one turned up thousands of candidate blue stars, and most of them were exactly that. What eventually singled out TON 618 for a closer look was follow-up spectroscopy, the same wavelength splitting technique described earlier in this story, applied to its light to check the properties astronomers expect from a genuine hot star. What that spectrum revealed instead was startling. Emission lines that did not match a star's expected chemistry at all shifted dramatically toward longer, redder wavelengths, to a redshift of a little over 2.2, among the largest redshifts measured for any object at the time. A star, however hot or unusual, does not produce a redshift like that. Only an object at a truly enormous cosmic distance, its light stretched by the expansion of the universe over the eons it took to reach Earth, could. TON 618 was not a star at all. It was a quasar, and one of the most distant and luminous ever identified up to that point, hiding in plain sight inside a catalogue built to find something else entirely. A redshift of about 2.2 corresponds to a light travel distance of more than 10 billion years. The light astronomers study when they observe TON 618 today left its source before the Earth, the Sun, and the rest of our solar system had even formed more than 4.6 billion years ago. Accounting for the universe's ongoing expansion during that travel time, an effect that further stretches the actual distance beyond the simple light travel figure, TON 618's present-day distance is substantially larger still, a genuinely difficult number to state with confidence, and one this story will treat cautiously rather than pin to a false precision. What matters for the rest of the story is simpler and better established. TON 618 is seen as it existed when the universe was a small fraction of its current age, and despite that almost unimaginable distance, and despite having been mistaken for an ordinary star for more than a decade, it remained bright enough in Earth's telescopes to register clearly on a modest photographic survey never designed to look for anything so extreme. That combination, extreme distance and extreme apparent brightness surviving the trip across it, is itself a clue to just how much light TON 618 must actually be producing at its source, a clue the rest of this story follows directly toward the object's mass. Subsequent decades of study, using the reverberation and virial mass techniques described earlier, turn that clue into an actual number, and it is a number placed on 618 almost immediately among the very largest black holes ever proposed. With TON 618 identified as a quasar rather than a star, and its extreme distance established, astronomers turned to the virial mass method described earlier in this story, combining the width of its broad emission lines with the overall luminosity of its continuum light to estimate the mass of the black hole producing that light. An early, widely cited study, published in 2004 by the astronomer Ori Shemmer and colleagues, arrived at a striking figure, roughly 66 billion times the mass of the Sun, a number that quickly made TON 618 one of the most frequently mentioned black holes in popular astronomy, precisely because it was so far beyond anything else measured at the time. That figure deserves the same honest scrutiny this story has applied to every large number so far. The single epoch virial method, as an earlier chapter explained, carries real uncertainty, commonly a factor of 2 or 3 in either direction, because it leans on assumptions about the geometry and motion of gas in the broad line region that cannot be directly observed at such distance. Subsequent studies, applying updated calibrations of the relationship between luminosity, line width, and mass, have in some cases produced somewhat lower estimates, with figures in the range of roughly 10 billion to 40 billion solar masses appearing in more recent analyses. Astronomers have not converged on one single, final number for TON 618's mass, and likely will not until a fundamentally more precise measurement technique becomes available for an object this distant, which may be a long wait. TON 618 is simply too far away for the stellar or gas dynamics methods used on nearer ultramassive black holes like Holmberg 15A to ever be applied to it. What every credible estimate agrees on, high or low within that range, is that TON 618 sits firmly in the ultramassive category described in the previous chapter, and likely near its upper end. Even the more conservative recent figures, around 10 billion to 40 billion solar masses, would place it among the handful of largest black holes known to science, comparable to or exceeding Holmberg 15A's direct measured 40 billion. The often quoted 66 billion figure remains a real, published scientific estimate, not an invention or exaggeration, but it is best understood as the upper edge of a genuine range, rather than a single settled fact, and this story will continue to describe TON 618's mass with that range, and that honest uncertainty attached rather than a single misleadingly precise number. Even the low end of that range is difficult to hold in mind by ordinary comparison. 10 billion is already larger than the current human population of the entire Earth, roughly 8 billion people. 66 billion, the high end of the published range, is more than 8 times that many people. A single object whose mass expressed in suns outnumbers every person currently alive several times over, compressed not across a planet's surface, but into a region of space that, as the next chapter will show, is barely larger than a solar system. That region, the black hole's event horizon itself, is where the story turns next, because a number this large, whatever its precise value within the published range, has to occupy a boundary of a very particular, calculable size, and that size is where TON 618 stops being an abstract number in a research paper and becomes something closer to a physical place, however alien, that could in principle be described the way any other location in this story has been. Take even the more conservative end of TON 618's published mass range, 10 billion times the Sun's mass, and apply the same Schwarzschild radius relationship introduced early in this story, that the boundary's size scales directly with mass, the Sun's own Schwarzschild radius being about 3 kilometers. 10 billion times the Sun's mass gives an event horizon roughly 30 billion kilometers in radius, which converts to about 200 times the average Earth-Sun distance, a unit astronomers call an astronomical unit. Pushed to the widely cited high-end figure, 66 billion solar masses, and the radius grows to roughly 1/300 astronomical units. Set either of those numbers beside the solar system's own layout. Neptune, the outermost known planet, orbits the Sun at an average distance of about 30 astronomical units. Even TON 618's more conservative event horizon, at roughly 200 astronomical units, would reach more than 6 times farther out than Neptune's entire orbit. The widely cited upper figure, roughly 300 astronomical units, reaches more than 40 times farther than Neptune, well past even Pluto's already distant orbit, out into the sparse, frozen region called the inner Oort cloud, the reservoir of icy bodies that occasionally sends a comet plunging in toward the inner solar system after a nudge from a passing star or the galaxy's own gravity. If TON 618, at the high end of its estimated mass, somehow occupied the center of our solar system in place of the Sun, its event horizon alone, before accounting for anything else about the object, would reach out past every planet and deep into territory currently occupied only by scattered distant comets. There is another way to feel the scale of a boundary that large, one that has nothing to do with planets at all: how long light itself takes to cross it. Light travels 1 astronomical unit, the Earth-Sun distance, in about 8.3 minutes. Crossing TON 618's high-end event horizon radius of roughly 300 astronomical units, at the speed of light, the fastest anything can travel, would take a little over 7 days. Put another way, if a beam of light started at the very center of that boundary and raced outward at the maximum speed the universe allows, it would still be traveling, still inside the black hole's own boundary, a full week later. Even the lower, more conservative estimates event horizon, at 200 astronomical units, would take light more than a day to cross. For comparison, light crosses the entire diameter of Earth's own orbit around the Sun in about 16 minutes. TON 618's boundary is not merely large by planetary standards. It is large enough that describing its size in kilometers, however many digits that number carries, undersells it far less than describing it in the time it takes the fastest thing in the universe to get from one side to the other. It is worth being precise about what that boundary actually contains and what it does not, returning to the correction made early in this story. Nothing about that boundary is reaching outward, grabbing, or sucking anything toward it from a distance. Any object safely outside TON 618's event horizon, even 1 astronomical unit outside it, would orbit under the same ordinary gravitational rules as a planet orbiting the Sun, determined entirely by mass and distance. What makes the boundary remarkable is not that it pulls harder than expected from a distance. It is simply that, packed inside an unremarkable-looking sphere, a little larger than the solar system's outer reaches, sits enough mass that the ordinary rules of escape, valid everywhere else in that same volume of space, stop applying entirely at that one specific radius. A boundary that size, holding that much mass, radiates an extraordinary amount of energy as matter continues falling toward it from outside, and that radiated energy is the next, and in some ways the most extreme number this story has to offer. Established at last, an object of somewhere between about 10 billion and 66 billion solar masses, its event horizon spanning a boundary wider than the solar system's outer planets, feeding on infalling gas the way every quasar described earlier in this story does. The natural next question is how much light that feeding actually produces, and the answer is what makes TON 618 more than a curiosity about size alone. It is, by most published estimates, one of the most luminous single objects ever identified anywhere in the observable universe. Bolometric luminosity, the total energy output across every wavelength of light an object emits, not just the visible portion, is the standard way astronomers compare the true brightness of very different kinds of objects, from stars to galaxies to quasars. Estimates for TON 618's bolometric luminosity run to roughly 4 times 10 to the 40th power watts, a number so large it is easier to grasp as a ratio to something familiar, the Sun's own luminosity. Expressed that way, TON 618 is commonly cited as radiating somewhere in the neighbourhood of 100 trillion times as much light as the Sun, from the earlier described accretion disk alone, a region no larger than a solar system, around a black hole whose own surface, the event horizon, emits no light of its own at all. Every photon in that estimate comes from infalling gas, heated by friction and compression, not from the black hole directly. Set that figure beside an entire galaxy rather than a single star. The Milky Way, home to somewhere between 100 billion and 400 billion stars of every size and brightness, most of them far dimmer than the Sun, has a total combined luminosity across all of those stars estimated at roughly 20 billion times the Sun's own light output. Divide TON 618's estimated luminosity by that figure, and the result is a single point of light, an accretion disk smaller than a solar system, outshining the combined starlight of an entire galaxy of hundreds of billions of stars by a factor of several thousand. That comparison is worth returning to directly. TON 618, by these published estimates, really is brighter than an entire galaxy of stars, not as a loose figure of speech, but as an approximate, order of magnitude accounting of actual radiated energy, the same kind of comparison Martin Schmidt made, with cruder tools, the moment he first understood what quasars like 3C273 actually were. It is worth restating the hedge this story has kept attached to every number in this range. TON 618's luminosity estimate depends on the same distance and mass uncertainties described in earlier chapters, and different studies, using different assumptions about the object's precise distance and the geometry of its accretion disk, arrive at figures that vary by a meaningful factor, even while agreeing on the essential picture, an accretion disk radiating on a scale that dwarfs entire galaxies. What is not in serious doubt is the order of magnitude. Whether the true figure sits nearer 50 trillion or nearer 150 trillion times the Sun's light, TON 618 remains, by any reasonable accounting, one of the most luminous single objects that current astronomy has ever measured, a point of light that has been crossing the universe, still visible, for more than 10 billion years. There remains one more question this story owes the object at its centre, a question less about its numbers, and more about what any of this would actually mean up close, if anything could ever get close enough to find out. Every fall toward a black hole this story has described so far, including the astronaut's fall through a stellar mass event horizon in an earlier chapter, ended badly and quickly, torn apart by tidal forces well before reaching the boundary itself. TON 618 and objects anywhere near its estimated mass would likely treat a hypothetical infalling traveller very differently, and the reason lies in a detail mentioned only briefly earlier. Tidal force, the stretching effect responsible for spaghettification, does not depend on a black hole's mass alone. It depends on how quickly gravity's strength changes over a short distance, and that quantity actually gets gentler, not harsher, as a black hole's event horizon grows larger. The reasoning is worth spelling out carefully, because it runs against intuition. A black hole's overall gravitational pull, at a given distance, scales with its mass exactly as expected. A more massive black hole pulls harder at any fixed distance from its centre, but the event horizon itself also grows with mass, at the same rate as the Schwarzschild radius relationship from earlier established. A traveller approaching a more massive black hole's event horizon is, in relative terms, approaching from much farther away in absolute distance, even though she is at the same relative position, right at the boundary. Tidal force weakens rapidly with increasing distance from the centre, faster than the overall pull weakens, and that combination means the stretching felt at the event horizon itself would decrease as the black hole's mass increases. For a black hole the size of TON 618's lower mass estimate, let alone its higher one, the tidal stretching at the event horizon would probably be so gentle that a traveller crossing it noticed nothing unusual there at all. No sudden discomfort, no warning, echoing the featureless crossing this story described for the boundary itself, but for a very different reason. Not because the boundary is inherently invisible, but because at this mass, gravity's local violence has likely been diluted across the length of a traveller's own body almost to nothing. That does not mean crossing would be survivable in any complete sense, and every claim in this paragraph carries the same honest hedge attached to everything else about TON 618 in this story. The featureless crossing at the horizon would not be the end of the danger, only a possible delay of it. Deeper inside, as the traveller continued falling toward whatever lies at the centre, described in an earlier chapter as a region where general relativity's own equations predict conditions no accepted theory can describe, tidal forces would presumably grow without limit eventually, just later, and over a longer stretch of falling time than for a small black hole. Current physics does not offer a confident, tested description of exactly when or how that would happen for an object this large, because no observation has ever tested general relativity's predictions in conditions that extreme, and the honest answer is that nobody fully knows. What can be said with more confidence is how long that fall might take, using the light crossing comparison from an earlier chapter as a rough guide. A traveller falling from just outside TON 618's event horizon toward its centre, at speeds necessarily below the speed of light, would likely take longer than the roughly week-long light crossing time calculated earlier for the boundary's own radius, plausibly days or longer of subjective falling time before reaching whatever the centre actually holds, an extraordinary contrast to the fractions of a second a similar fall would take inside a small stellar mass black hole's much tighter boundary. Whatever might await at the end of that fall, the fall itself for an object this large would not be sudden. It would be one of the longest, strangest journeys physics can currently imagine any object taking, through a boundary too gentle to notice, toward an ending too extreme for any existing theory to fully describe. That combination, gentle at the edge and unknown at the centre, closes the physical story this episode set out to tell. What remains is the honest state of the science itself. How sure astronomers actually are TON 618 holds the record this story's been building toward, and what the honest answer to that question reveals about the largest objects the universe may be capable of building at all. Every number this story has attached to TON 618, its mass, its size, its luminosity, has carried a hedge, and the final honest question is simple. Is TON 618 actually the largest black hole known, or merely the most famous one? The answer, at the level of current published science, is genuinely unsettled, and that is worth sitting with rather than smoothing over. The widely cited 66 billion solar mass figure comes from an early single-epoch virial estimate, a method this story has repeatedly flagged as carrying real uncertainty, a factor of 2 or 3 in either direction. More recent reanalyses have suggested figures as low as roughly 10 billion to 40 billion solar masses for the same object, using updated calibrations of that same method. Meanwhile, Holmberg 15A, described earlier in this story, has a mass of roughly 40 billion solar masses measured by direct stellar dynamics, a method carrying considerably less uncertainty than any virial estimate, because it does not depend on assumptions about gas cloud geometry billions of light-years away. Depending on which of TON 618's published mass estimates one trusts, either object could reasonably be called the more massive of the two. A handful of other quasars, including one catalogued as S5 or plus 81, have also been assigned virial mass estimates in the tens of billions of solar masses, with the same caveats attached. There is at present no single object universally agreed to hold the title of most massive black hole known. There is instead a small cluster of extreme candidates, TON 618 prominent among them, whose exact ranking depends on which measurement method and which study's calibration of it is trusted most. There is a deeper question hiding underneath that ranking dispute, and it may matter more than the ranking itself. Is there an upper limit to how large a black hole can actually grow? Some theoretical work, building on the accretion physics described earlier in this story, has suggested there might be. An accretion disk feeding a sufficiently massive black hole may become gravitationally unstable at a certain radius, dense enough for its own gas to collapse locally into stars, rather than continuing to fall smoothly inward, a process that would throttle the black hole's own fuel supply once it grew large enough. Some researchers have proposed that this self-limiting effect caps plausible black hole growth somewhere in the range of tens of billions of solar masses, coincidentally close to where TON 618, Holmberg 15A, and the other leading candidates already sit. If that theoretical ceiling is real, and it remains a hypothesis rather than settled fact, then TON 618 and its handful of rivals may not simply be the largest black holes astronomers happen to have found so far. They may be close to the largest black holes the universe's own physics permits any galaxy to build at all, at least by the ordinary channels of accretion and merger this story has traced from a single collapsing star all the way to this point. That is where this particular thread of astronomy currently stands, honestly uncertain at the edges, but resting on a chain of well-tested physics all the way down: escape velocity, the Schwarzschild radius, the collapse of a dying star's iron core, the orbital mechanics that weighed Sagittarius A star, the accretion physics that lights up every quasar ever found. 618 sits at the far end of that chain, not because it broke any of those rules, but because it may be one of the most extreme, honest results of applying them consistently, across billions of years and billions of solar masses, to see how far gravity's oldest, simplest trick, mass overwhelming its own resistance to collapse, can actually go. A single point of light, first mistaken for an ordinary blue star in a 1957 photographic survey, has turned out, on the best evidence currently available, to be brighter than an entire galaxy of stars, and to hold, somewhere within its own honestly uncertain range, one of the largest concentrations of mass the universe is known to contain. Whether it holds the outright record, or simply sits near the top of a small, extreme cluster of rivals, may never be fully settled from 10 billion light-years away. What is settled is the physics that got this story, and every astronomer who has ever measured a black hole's mass this far. This story began with a simple fact about gravity: fast enough and nothing escapes it, not a rocket, not light itself. Every chapter since has been a variation on that one idea, scaled up by factors of 1 billion or more, from a dying star's iron core collapsing in under a second, to the supermassive black hole quietly anchoring our own galaxy, to a single point of blue light, catalogued by accident in 1957, that turned out to outshine an entire galaxy of stars from more than 10 billion light-years away. TON 618 may or may not hold the exact record for the largest black hole ever found. Honest astronomy keeps that question open, and probably will for some time. What it demonstrates regardless is how far a small number of simple, well-tested physical rules can be pushed, and how much of the universe's most extreme behavior turns out to follow directly from the same gravity that holds a person's feet to the ground and a planet in its orbit, given enough mass, enough time, and enough patience from the astronomers measuring it from an unimaginable distance. Sagittarius A star sits at the center of the galaxy overhead tonight, doing the same thing TON 618 does, only far more quietly. The physics connecting the two is the same physics this episode traced from the very first thrown ball. That, more than any single number, is the actual scale of the story.